Hi, good day. In this video, we'll look at elastic collision in two dimensions. Of course, we have done video on elastic collision in one dimension. You can check the video in our playlist. So here, as we can see, we have two billiard balls. Let's say this is a ball, billiard ball. You have another ball. This is ball 1, this is ball 2. This is stationary. Ball 2 is stationary. So the initial velocity of this ball 2 is 0. So as this moves, this ball 1 moves and hits this ball 2, it is said that this ball 2 moves at this angle theta 2 in this direction, while ball 1 moves at this angle in this direction. So this v1 is the final velocity of body 1 and v2 is the final velocity of ball 2. So we want to treat the conservation of linear momentum here, but in this case now this involves two dimensions. So we are going to resolve this in two dimensions. We'll resolve it vertically and horizontally. So let us consider the horizontal part of the motion. The horizontal part of the motion. So we know that for momentum to be conserved, the initial momentum before collision should equal the final momentum after collision. That is, if the collision is isolated, if there is no net external force in the system. So looking at this, the momentum, this is in horizontal direction. So this is just in one direction. So the momentum of this ball 1 will be m1u1. Of course, this is horizontal motion we are considering. So once it meets this body 2, we have the momentum for body 2. This is m2u2, and of course this is 0 because it's not having any momentum, it's stationary. So this equals the final momentum will be, we are considering the horizontal part of the motion. So let us find the momentum, this final momentum m2v2 along this horizontal, taking note of this angle theta 2. So we can bring this out. This is like this, so this becomes the theta 2 and this is m2v2. Of course, if I want to resolve this, I can call this x. If I want to resolve this horizontally, this of course will be m2v2 cos theta 2 using SOHCAHTOA. Of course, if I say cos theta 2, it will be adjacent upon hypotenuse, and the adjacent is x and hypotenuse now is m2v2. So we arrive at this. So the momentum of body 2 after collision will be, the momentum of body 2 after collision will be, this will be we got it to be what, m2v2 cos theta 2. Of course, since we are considering horizontal motion, we take this side as positive and take this side as what, negative. Of course, this is still in the opposite direction. So we can take our axis here. From here, this becomes our positive, and if we are going back, this becomes our what, negative. So similarly here, we take the upper part as positive and take the downwards as what? Negative. So going further, so it means that we are taking this side as what? Positive. So we have for body 1, the momentum will be, so still resolving this, finding the horizontal component. So let us find the horizontal component of this body 1 after collision. So this is, I call it body because we're talking of ball, so I can use body. So if I say body, you know I'm talking about the ball. So the final momentum of this ball 1 after collision will be, so I can label this y. Now I bring this out, this is looking like this, so I have something like this. This becomes theta 1. Let's label this y. This is m1 v1. So of course this is where I'm looking at, so this becomes the opposite of this angle, and this becomes the opposite of this angle. This becomes the hypotenuse, and this becomes the what? The adjacent. So our interest is still to find the horizontal component. So if I say cos theta 1, it will be adjacent upon hypotenuse. So this again becomes m1 v1 cos theta 1. So we have, this becomes plus m1 v1 cos what? Theta 1. So this is the conservation of momentum for this horizontal motion. So have it as plus m1 v1 cos theta 1. So this is the horizontal conservation of momentum, okay, showing that the momentum before collision equals the momentum after collision for this x axis, x direction, the horizontal part of the motion. Let us now find the vertical part of the motion. Of course, you see that when this ball is moving, it is horizontal, so it doesn't have a vertical momentum, so we'll say it is 0. The vertical momentum is 0, so that we have something like this. This becomes 0 equals, we say that we take this upper part as positive. So let us find the vertical component of this. So we can label this now. This becomes the vertical component. So if we use the horizontal component as x, so let us label the vertical component as p, so that we say this is opposite upon hypotenuse. So this becomes, let's clean this. So this becomes, this is opposite upon hypotenuse. So we say sine theta 2 equals opposite upon hypotenuse. So this becomes that p equals m2 v2 sine theta 2. So this is m2 v2 sine theta 2. So this is the vertical component of this momentum. So we look at the downside, look at this. So this is in the negative. So we say, we'll still bring it out. This is this. And we are looking at the vertical. So this is theta 1. This is m1 v1. So let's label this one q, so that we have, this is opposite upon hypotenuse sine. So sine theta 1 will be opposite upon hypotenuse. So that we have that q is m1 v1 sine theta 1. And since this is downward, we take the upper side as positive and this as what? Negative. So we are considering from here, we take this as positive and take this as what? Negative. So this becomes minus m1 v1 sine theta 1. So this is the equation for the conservation of momentum for two billiard balls that collide that collided elastically. So you can always solve this simultaneously to find the missing values. You can solve, if we call this equation 1 and call this equation 2, you can solve this simultaneously to find the missing values. Of course, we shall solve a problem to illustrate this. So we shall be solving this problem. These are the problems we'll be solving. This is one of the problems. This is another problem. So you stay tuned. So if this is your first time of watching this video, do well to give it a like and subscribe for future updates.